Could we ever build a telescope powerful enough to see the age of reionization? Could we play disc golf on the moon or Mars? And why do rockets launch near the equator? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops into your brain, just write it down. I'll gather them up and I'll answer them here. All right, let's get into the questions. Snort World. Would it be possible that one day we could build a telescope powerful enough to see the opaque stage of the early universe? So I actually did a follow-up with Snort World just to make absolutely sure I was going to be talking about the right thing, but I'll sort of describe the entire process as well. So we get the beginning of the universe, the Big Bang, blah, 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 right? And then you get the first 380,000 years or so where the entire universe was ionized. It was like plasma. It was like the surface of a star. And then it had cooled down to the point that photons could start escaping out into space. And we see that today as the cosmic microwave background radiation. And that is the earliest that our telescopes can see. You can't make a more powerful telescope that will let you see beyond the cosmic microwave background radiation. I think you all know that. But there is another phase. So if you then progress forward in time, then now the universe is continuing to cool. All of that hot plasma dissipates as plasma and is now turned back into just atoms of neutral hydrogen and helium, just vast clouds of this primordial elements just out there in space. And it is dark. And so astronomers call this the Dark Ages, and it lasts for a while. And then you get this point where all of that primordial hydrogen helium is starting to collect gravitationally into larger and larger objects, the stars, right? And after a while, you get collections large enough that you get the first stars forming, these population 3 stars. And you get more population 3 stars, and more of these stars. And then those stars are putting out enormous amounts of ultraviolet radiation. And it is sort of so pervasive that that light gets out and it starts to re-ionize all of that gas that was out there. And it hadn't found its way into a star. And that's most of the gas now was lit up again, turned back into a plasma. And so the problem is that these first stars, were shrouded in all this gas and dust. We're sending out that ultraviolet radiation and we're turning the entire universe back into another version of what you had before the cosmic microwave background radiation was released. And so the problem is that we can't see those first stars because they are cloaked in this ionized gas that is everywhere. And so the question you asked is could we ever build a telescope powerful enough to see that stage of the early universe? And the answer is no, that we couldn't build a telescope powerful enough because it is opaque to telescopes in the same way that the cosmic microwave background was opaque to telescopes, but not all wavelengths. So there is a couple of tricks that can be done. So the first thing is that, during the Dark Ages, you just had vast clouds of this neutral hydrogen, and neutral hydrogen gives off a very specific signal in the radio spectrum. It's very unlikely, but if you wait large amounts of time, then you're gonna get sort of one of these atoms in this vast cloud release this spectrum of radio waves. And they call this the 21 centimeter line. Now, of course, over time, what was the 21 centimeters when it was released? That's the length of the wavelength, so 21 centimeters, so like about this much, right? But over time, because of the expansion of the universe, that light has been red-shifted out into the radio spectrum. And so the right tool, and this wavelength can pierce through this ionized material and actually reach us, but the signal is very faint. And so the plan is to build really powerful radio telescopes that are capable of mapping this neutral hydrogen that is giving off the 21 centimeter line. And what you're going to see is concentrations of hydrogen. You're going to see the places where you've got proto-stars starting to form, that first generation, the population 3 stars, concentrations. You're going to see knots and twists where those first supermassive black holes were starting to form as these various stars were detonating a supernova and their material was coming together at a time when the universe was opaque, that we couldn't see. You're going to see knots and clusters of neutral hydrogen. But the problem is eventually all of that material became ionized. And so then you can no longer use that as a way. And you got to wait for the universe to continue to expand, for the stars to push away all of that additional material. And then things can look more like the universe that we see today. And that next stage, that next phase after the stars, those first stars had formed and died and pushed away that material and things had cooled down a bit more, that's when our first optical surveys of the universe come online. The kinds of things that Hubble can do, that James Webb can do, is you can actually start to see those first galaxies. But there is a wall behind those first galaxies that even our most powerful telescopes can't get to. And it's only radio telescopes that will allow us sort of one tiny glimpse into the time before leading into the age of reionization. I'm sure you noticed the Stargate planet name that appeared above my shoulder. And if you didn't, it's up here or here. And this is a way for you to vote, for you to tell us what you thought was the coolest question of the week. And so we're going to put a different Stargate planet name. Of course, you remember them all, right? We're going to put the Stargate planet name up above my shoulder for each one of the questions. And then once you finish watching the entire show and you've decided what you thought was the best question, just go ahead and put the text of the planet name into the comments and then ask the rest of your question or whatever, and we'll count up and we will celebrate. And so the winner last week was Jay Steiger. What is the speed limit that can be achieved by slingshotting around planets? And we had a really interesting conversation about that and doing slingshots around black holes. So thank you for everyone who voted for last week. Don't forget to vote. Hengehog838. Let's put disc golf course on the moon and Mars. How would frisbees fly differently? Inside a crater, we could have baskets. So if you tried to play disc golf on the moon or Mars, it would be largely a disappointing experience. The moon would be the worst, and then Mars would still be terrible, but you could try to make it work. So on the moon, there is no air. And so the way that a flying disc works is that it gets lift from as it's turning and as it's moving through the air, it's getting lift, it acts like a wing, and it allows it to fly a lot farther than if you just threw it ballistically. But on the moon, there is no air, and so it just will fly ballistic. However far you can throw the disc is how far it's going to get. Now, on Earth, you want to throw it very flat. It's all about the angle that you throw the disc, and then it sort of hits the air in the right way and it gets as much lift as it can and it flies along. On the moon, you would want to throw it at a perfect 45-degree angle. That's the angle that'll get you the most of a trajectory. But essentially, throwing it is exactly the same as you throwing a ball that weighs the exact amount as the disc itself. There's no benefit from throwing it on the moon. Now, if you flew it on Mars, then you've got a bit of a compromise. So the gravity of Mars is 1/3 the gravity on Earth. And that means that you could throw the disc for 3 times as far if it had the same atmospheric density as Earth, but it doesn't. It has 1% the atmospheric density of Earth. And so it's going to feel like if you throw it, that it's going to be about 33 times heavier than if you threw it on Earth. Like, it's not going to feel that heavier in your hands, but it's going to want to take a trajectory that is like that. Now, if you threw it hard enough and fast enough and at the right angle, you could get a little bit of lift, but it's still going to just fall, and you're still probably going to go for that 45-degree angle to get the maximum flight distance that you can get. No, the place where you want to play disc golf is on Titan, place where you've got an atmosphere that is thicker than the atmosphere that we have on Earth, where the gravity is a fraction of the gravity that we have on Earth. And so you could throw your discs and they would go for at least 3 times, 5 times farther than what you could throw them on Earth. It would be amazing. I mean, you could strap on a pair of wings to your arms and you could fly around on Titan, which is like just another reason to go to Titan. Korax Catcher. How much more cargo could a rocket lift if it were launched from the equator versus Texas or Florida? Wouldn't it be more efficient? Absolutely. The equator is the best place to launch a rocket, assuming that you want to launch in the same direction that the Earth is flying and you want to launch into an orbit that is directly overhead the equator of the Earth. And so when you think about the Earth is spinning about 1,650 kilometers per hour. And to be orbital velocity, if you're like to be going around the Earth fast enough that you're not going to then crash back down into the Earth, you need to be going 28,000 kilometers per hour. So you get this sort of savings that to actually sort of reach the gap between the speed that your rocket is going on the ground to the speed you reach at your maximum rate. There is that gap that you need to fill with your propellant. And so if you launch really close to the equator, then you get that bonus 1,650 kilometers per hour that, if you'd have to make up in some other way. But you only get that if you're going in the same direction the Earth is turning and if you're trying to launch into a place that's just above the equator. If you want to go in the opposite direction that the Earth is turning, then you have to counteract the rotation of the Earth and you have to launch it with an extra 1,650 kilometers per hour. And if you want to go into a polar orbit, so you're not going with the equator, but you're going above and below the Earth, then you don't get any benefit whatsoever. It's only if you're doing that flight. And a lot of people ask, like, why aren't all of the launch sites on Earth just at the equator? And the problem is there aren't a lot of great places which are at the equator that would be easy to launch from, but are also very close to industry that are, in the United States or in China or in Russia. And so like for Cape Canaveral, which is in Florida, which is like one of the most southern parts of the United States, they get about 90% of the benefit of if they were down at the equator. So like that's good enough for when you think about the fact that it's on the east coast of the United States. When they launch rockets, they go out over the ocean. It's safer to launch rockets over the ocean. It's easy. It's flat out at Cape Canaveral. It's easy to get rockets out to the launch platforms. You don't have to think about trying to launch your rocket from the top of a giant mountain. There are places on Earth, like you could launch rockets from the top of Kilimanjaro and it would be more effective. But if you sort of considered all of the costs and building a road up Kilimanjaro and so on and so forth, it's better to just launch from a place like Cape Canaveral. But there are companies that launch rockets from the ocean, or there were, one was called Sea Launch, and they would put your rocket on a barge, take it down to the equator, and launch from the equator. But they're just, when you consider all of the costs, moving the rocket to the equator, bringing it back with the barge and all that, in the end, it's just easier to just have infrastructure, nearby where you're going to launch. Todd Ablett. So if Starship could take 10 diameter telescope discs, could you assemble a bunch of these in low orbit and have like a 60-meter diameter telescope with no atmospheric interference? So there's two ways to approach this issue. One is if you want to just use the combined light of the different telescopes. So for example, if you launched a bunch of telescope mirrors on Starship and you put them into space and they were side by side and they were just kind of drifting nearby, you weren't really thinking too much about how far apart they are, then you could point both of those telescopes at one target, say some distant system, and you would get the equivalent of the total surface area of the two telescopes, which is good. I mean, you're getting twice the surface area if you just use one, but there's a few downsides that you would need to work with. I mean, the two telescopes are going to be experiencing just slightly different changes in radiation heat. So they're going to have different amounts of sort of flexing from their heating and cooling. And so it's going to be a little tricky to sort of really pair up and make sure that you're getting the same amount of data from the two telescopes. And so it's not a perfect solution. I mean, even James Webb has to deal with this kind of thing, but it would be pretty good. And then each time that you added one more of these telescope mirrors, you could just add these to the network. And so you add a third telescope, now you've tripled your surface area. You add a fourth one, now you've quadrupled your surface area. You just get yourself all the way up to whatever you want. And sort of the advantage of that is they could all look at the same target, or they could all look at different targets. And so you could sort of parcel out these telescopes. And this idea has been explored quite a bit. There's a mission that I really like called Nautilus, which sort of proposes doing exactly that you launch these sort of flat discs, you stack them up inside Starship, and they wouldn't be 10 meters. Maybe they're 8 meters to sort of fit within the fairing, and maybe you could fit 10 of them in one Starship. And then you launch them all, and then they inflate. And then they're these sort of balls that are floating in space, and they can kind of turn and look at the same target, or they can turn and look at different targets. And they might use sort of different optics than mirrors. They might use like a lens, like a Fresnel lens or something like that. So that's pretty cool. Now, the other path that you can go, and this one is more exciting, is that you build an interferometer. So if you can lock down the distance between the two telescope mirrors, either like with a rigid, connection in between them, a strut, or you can control the distance using propulsion so that you can remain within, and this is the key, the same wavelength. So you have to be receiving the same wavefront. Essentially, you need to be within a few hundred nanometers of each other and maintain that position as long as you're doing your observing. And if you can do that, then you get to have a telescope that is the equivalent resolution as the distance between those two telescope lenses. And so if you launch the two telescopes and you don't control their position, then you get the equivalent of, two 10-meter telescopes. But if you do control them and you hold them 100 meters apart, you now have a 100-meter telescope. For resolution, you don't get the light gathering ability. And so for fairly bright objects, it would be as if you had a 100-meter telescope that was looking at some target. So there's a lot of different ways that we can take advantage of multiple mirrors flying on the same mission. And I hope that there will be, look into the Nautilus mission. I've done an interview with the principal investigator for that. Yeah, we could have some future where there's just this giant fleet of telescopes operating together, and just as you throw up more of them in there, this whole network just gets better and better. FPL Mikael, is it true that when the Milky Way and Andromeda collide, there will only be a total of 40 to 50 galaxies visible, as everything else has moved too far away for even light to reach us? That's kind of true. So yes, the Milky Way and Andromeda are probably on a collision course with each other. We've done some reporting that maybe it'll be a close flyby and they won't merge for a few extra billion years. But at some point between 7 to 10 to 15 billion years from now, Milky Way and Andromeda will finally catch each other and they will merge into a larger elliptical galaxy. And they will gobble up the various dwarf galaxies, and the galaxy in Triangulum M33 will also join the party. And so we will get the entire local group into one large elliptical galaxy. And an example of this is M87. That is a galaxy that has completed becoming a giant elliptical galaxy. And then star formation will slow down and the galaxy will just sort of become red and dead, as they say. And all this time, the expansion of the universe has been continuing on, and the galaxies are accelerating away from each other off into the universe. And so the wavelengths that we use to be able to perceive those other galaxies just keeps shifting into the red. Even right now, like we want to see the cosmic microwave background radiation, it is shifted from what was originally red. The CMB looked like the surface of a red star, and it is now shifted all the way into the microwave thanks to the expansion of the universe. And so our ability to see those galaxies, they will shift from visible light into infrared, from infrared into microwave, from microwave into radio, and the wavelengths will just get longer and longer and longer. And it will appear as if the entire universe has just kind of fallen over the cosmic horizon. But that'll take about 100 billion years. So, let's say we'll turn into our Milkdromeda in 10 to 20 billion years when we've finally slurped up all the dwarf galaxies. But then we'll still see the universe for another, say, 80 billion years after that. And, people always say like, oh, it would be so sad. Future astronomers would live in this universe. And they wouldn't know that there was a history to the universe. And that's true if they have rudimentary technology, but they'll build more and more powerful radio telescopes. And eventually they will detect the presence of galaxies that are redshifted out to oblivion. And with even more telescopes, they'll start to piece together the history of the universe. It would take trillions of years before this expansion truly redshifted those photons till they were indistinguishable from the background of the universe. Nick Stokes, does Hawking radiation affect dark matter? If not, could we have dark matter only black holes in the far future? So, we don't know if Hawking radiation actually does exist. But if it does exist, this is this process where black holes evaporate over vast periods of time. But what the evaporation product is mostly photons. And so if you look at a black hole and you have sort of removed it from all external sources and you're watching the radiation that's coming off the black hole, then you're going to see heat coming off the black hole. It's going to be just the occasional photon here. Yeah, every now and then you'll get a more complicated molecule is going to come off a black hole, a proton every now and then, but mostly it's just going to be photons. And so what impact does radiation have on dark matter? And it appears that dark matter and radiation don't interact with one another except through gravity. And it seems really weird to say like radiation affecting dark matter through gravity. Well, according to E=mc², you can take any amount of radiation of photons, you run them through E=mc², and that tells you the equivalent of the mass, and that's the amount of gravity that light produces. And so light, theoretically, is going to be pulling on dark matter and shifting it around, but not by very much compared to what mass is doing. And so you're asking, like, could you have dark matter only black holes in the far future? Well, the thing is that like black holes are just made of black hole. So you don't really distinguish between what a black hole is made of. If you take matter, you put it into a black hole, you get black hole. You put antimatter into a black hole, you get black hole. You put energy into a black hole, you get black hole. And theoretically, if you put dark matter into a black hole, you get black hole. So there's no distinguishing between them. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Xander Edwards, Wayne Guy, TP, Charles Taylor, Chris Luskar, Bill Peterson, Wolf Michael, Mark Brinkhouse, Andre Ledreau, Michael and Suzanne Costin, Yo Seidman, and Bill Kerr. Join the club at patreon.com/universetoday. Johnny Appleseed. Will we ever send out another Voyager mission with upgraded technology, or have we already? So the Voyagers were launched in 1977. They quickly did their flybys of Jupiter, Saturn, and Voyager 2 went on to do flybys of Uranus and Neptune. And then both Voyager 1 and Voyager 2 are off into deep space. So has there been another spacecraft that has followed the same journey as the Voyagers? And the answer is no. The closest example that you can get is New Horizons, which did a flyby of Jupiter and then went off to see Pluto, and has then done a flyby of another Kuiper-Belt object since then. And then apart from that, there have been no objects that have been sent on interstellar flights the way the Pioneers, the Voyagers, and New Horizons have gone on. But there are plans to build a new interstellar mission. The spacecraft currently is called the Interstellar Probe. And the plan, although that sounds really cool, right? Because let's build our probe that can cross the stars. But no, it's just to get to interstellar space, which is, where the main effects from the sun, where the solar wind is expanding away from the sun and reaching the interstellar space, the place where the solar winds from all the other stars are out there. And there's this giant bubble that surrounds the solar system because the sun is pushing out with its solar wind. And the Voyagers have reached interstellar space. They've gone beyond the heliosphere and they're out into interstellar space. And so now, based on the sort of hints that we've gotten from the Voyagers, astronomers want to build a proper mission that will go out to interstellar space and explore. And so, we know from the previous episode that you want to use gravitational slingshots to give you more velocity. And so absolutely, I would expect that if they did end up building an interstellar probe, it's going to do a gravitational slingshot of at least Jupiter, probably Jupiter and Saturn, and then maybe something else if they can line it up. But the other idea that's really interesting is you can actually use the sun to do a slingshot. It's a thing called the Oberth maneuver. And essentially you fly down towards the sun, and when you reach the closest point of your orbit around the sun, that's when you kick in your thruster, and it sort of multiplies the final velocity of your spacecraft. And so you can imagine a spacecraft falling down into the sun, firing its thrusters, doing this slingshot around the sun, maybe going back in time and saving the whales, but maybe not, and then flying past Jupiter, getting a gravitational assist, flying past Saturn, getting a gravitational assist. And so maybe we could have the spacecraft get to interstellar space within a decade, within 15 years, like something that is a lot quicker than it took for the Voyagers to make the journey. But apart from that, nobody is planning on sending another mission. And partly it's because the planets aren't lined up again. I mean, there was this once in 150 year fluke that you got all of the giant planets lined up in a way that you could make a gravitational assist past all of them. And that's just not going to happen for another 100 years. Edward Hinton, do we hypothetically live forever if the universe is cyclical? So the idea of a cyclical universe is sort of a flavor of, cosmology, the origin of the universe. I mean, right now, the overwhelming evidence is that the universe began as we know it 13.8 billion years ago, and at a time when the universe was a lot more dense than it is today. Objects that are currently more than 90 billion light years across were this far apart. And yet now they've expanded out over, of course, the 13.8 billion years to get to this current size. And the question always is, what came before, right? What started that process in motion? And so one answer is that there is nothing before, that the universe was always at this point when it was as dense as it was before the Big Bang happened. And then for some reason, the Big Bang happened and the universe started to get less dense. And we don't know why. And so it doesn't necessarily mean that there was anything interesting happening before the Big Bang, that you had this infinite amount of time where the universe was a certain density, and then you had this, for some reason, it began to become less dense over time. So that's one possibility, right? The other possibility is this idea, as you say, of a cyclical universe, that that at some point as our universe progresses, some event will happen that will sort of start the process all over again, that a new Big Bang will open up within the current Big Bang. And, there's no reason to believe that's the case. I mean, there's no evidence that says, okay, yeah, here's a place where we can see some kind of artifact from the previous universe. We don't see that. And so, it doesn't mean it's not possible, but, lots of people are sitting and trying to think of ways that might be the case, but there's no evidence that it is. So, but then, you say would we live forever? Right. And what does it mean if you aren't actually physically together in one piece and experiencing continued consciousness? Right? You are made up of the various atoms of all of the people that have lived before you. There's some number of atoms that are in you that were once in Genghis Khan. So is Genghis Khan living forever inside of you? I would argue no. I would argue he died and he is not around to appreciate existence any longer. You're currently enjoying those atoms, and eventually you will give them up and somebody else will take a turn with the atoms that make up your body. And if there is a cyclical universe, and who knows, atoms might not survive the journey from one thing to the other. Maybe it'll be all of the atoms will be turned into energy or some other exotic form of matter, and then that will be turned back into atoms. Is that living forever? So, I really think it probably just depends on how you want, the definitions that you want to use. My feeling is no, you live as long as you live and then you're dead. Michael D. FPV. Have we seen Oort clouds of other solar systems? So the Oort cloud, this is this giant cloud, spherical cloud of icy objects around the solar system. And it extends really far away. probably out to at least 1, maybe 2 light years away. It could very well be that the Oort cloud from the solar system is getting close to the Oort cloud from Alpha Centauri, if Alpha Centauri has an Oort cloud. And the only way that we know that the Oort cloud exists is that we see objects, these icy objects, comets, that are falling down into the middle of the solar system on trajectories that if you sort of calculated the entire trajectory of the comet, then it would tell you that they're out 50,000 astronomical units from the sun, 100,000 astronomical units from the sun. And the problem is that we can't see our own Oort cloud. It is the closest Oort cloud to us, and yet we really cannot see any of the objects in the Oort cloud until they are starting to fall into the solar system. Really, we don't see these comets until they're passing the orbits of Saturn, say. When enough radiation is reflecting off of them from the sun, they're starting to grow a tail, they appear. And we see them at the last minute. And that's kind of what makes these comets so dangerous. I mean, we may map out all of the near-Earth asteroids, every potential asteroid that has our name on it, we could move them all into very safe orbits, and yet a comet could come out of nowhere within a few months and crash into the Earth. So, I always am so excited about our ability to protect Earth from asteroids, and yet the comets are going faster. So that's another problem as well. But anyway, so no, we can't see our own Oort cloud. And we just don't have telescopes big enough and powerful enough to be able to see them. So think about it. We can see objects in the Kuiper belt. We can see objects that are maybe a few 100 kilometers across, where they are, say, 90 astronomical units away, like the very limit, 100 astronomical units away. 200 astronomical units away. I mean, I forget what the farthest is, far out, but you're in the hundreds of astronomical units. But you would need to be able to see into the tens of thousands of astronomical units to be able to see the Oort cloud. So we don't see any other Oort clouds. We don't even see our own Oort cloud. Now, there are hints of seeing Kuiper belts in other star systems, and there are definitely large rings of icy material surrounding other stars. Maybe what if Saturn was instead replaced with a giant ring of icy objects around the entire star, that kind of thing. But no, we can't see the Oort clouds. Miliano Lineri, do you think that Earth's resources are going to be enough to support new business space models such as SpaceX? I mean, it always just depends on how much of the Earth's resources any one industry is going to use. So when you launch a rocket, you have the raw material that went into building the rocket. In the case of Starship, it's made of stainless steel. So what is that? It's like iron and chromium. You've got the propellant, which in the case of Starship is methane. And then you've got the sort of insults to the planet that the technology is doing. And so in the case of Starship, you've got this skyscraper filled with methane that you are burning, and you are pumping out all of the greenhouse gas and some of the leftover methane, which is another greenhouse gas all on its own, into the atmosphere. And right now, one Starship flying every year, 2 Starships flying every year is no big deal. I mean, it is a fraction of a fraction of a fraction of the amount of carbon dioxide and so on that is put out based on, cars driving and so on. But if we see hundreds of launches a day, then yeah, that's going to have a big impact on the environment. Now, the potential good news is that methane, unlike regular fossil fuels, can be synthesized. You can run a giant chemical plant where you are using solar energy, you are pulling carbon dioxide out of the atmosphere, you're mixing it with hydrogen from water, and you're creating methane in a way that is carbon neutral. And Elon Musk has said that this is a thing they would like. This is an aspirational goal that they would like to get to. But it's so cheap to just go and buy methane at the methane store and use that. And so that's the technique that SpaceX has been using today. But assuming that carbon emissions continue to be sort of regulated and ratcheted up, eventually you'll get to a point where it makes the most sense. The most economic sense for SpaceX is to make their own methane in a way that is carbon neutral. But I don't think that we're going to ever get to this place where we are needing to launch hundreds of rockets a day. That as we develop our space-based infrastructure, as we build more manufacturing in space, as we acquire more resources in space and we move them into places where the manufacturing is being done, I actually think our need to launch things from Earth out into space is going to decline. That why launch fuel when you can gather fuel in space and use it in space? Why launch building materials to the moon when the moon is made of building materials? And so I actually wouldn't be surprised if we get to this place in the far future where we don't do a lot of rocket launches at all. Really, it's just to take humans from space to Earth, from Earth to space. And if the rocket is fully reusable, which, that's the plan for Starship, then you don't have to go through throwing out your rocket every time you launch. So right now, I don't think that we're going to be staring down a large impact on the environment compared to all of the other things that we currently do that impact the environment: driving, transportation, growing food, it goes on and on and on. And still the kinds of regulations designed to curb emissions will apply to rocketry as well. So, I am less convinced that there's anything that would support new space business models. That, we find that in general, space business models don't work. They don't make money. And, apart from launching communication satellites, weather satellites, science satellites, things like that, nobody's been able to figure out a way to make money from space. And that is probably going to last for a long time. So I wouldn't worry that hyper capitalists are going to come along and make a ton of money in space. It seems that all they do is just lose a ton of money and then go out of business. And I think that'll continue for a while. Nameless. Will you ever cover theories that don't have a Big Bang origin? Absolutely. If a theory came along that better matched the preponderance of evidence that we see in the universe, I would gladly cover it. When you think about the evidence that we have for the universe, we have multiple independent lines of evidence. So the first big piece of evidence is that the universe is getting less dense over time. In every direction that we look, galaxies are moving away from us. And so if you look out and you see people running away from you in all directions, right? And, this is just a snapshot. You get a 1-second clip of everybody being, in all directions running away from you. And then you run the clock back. Then you imagine that everybody was closer to you a little before that and a little closer before that, right? That's a very weird analogy. But anyway, so if we run the clock back, then things were closer together in the past. That is expansion. That is, the universe becoming less dense. That is right away, no matter what you have to account for the fact that everything is getting less dense over time. Second, you have to look at the percentages of elements that are in the universe. About 75% of the universe is hydrogen, and about 25% of the universe is helium with trace amounts. So for some reason, there is this 3-to-1 ratio of hydrogen to helium throughout the entire universe. That's a weird number, right? But if you take the increasing size of the universe, the decreasing density of the universe over time, and you run that clock backwards and you just make everything closer and closer and closer together and closer together, you eventually get to this place just a few minutes after the Big Bang where the entire universe was like the interior of a star. And we know in a star, you get hydrogen being turned into helium, and you get a certain amount of helium as a byproduct. Well, if you sort of run this process for about 10 minutes, you get the ratios of hydrogen to helium that we see. That's a huge piece of evidence that how could we get those ratios if that stuff wasn't the equivalent of the interior of a star for a certain amount of time? So another data point that the universe was more dense in the past, less dense in the future. And then we look at the cosmic microwave background radiation. We have this time when you have this radiation that was being let off into the universe for the first time. And so before that, the universe was opaque and would have been shining in red because it was so dense, again, denser in the past. And now, because of the expansion of the universe, the wavelengths have shifted. We see them in the microwave. Another really important data point. You get this timeline. Now, everything moving away from us. 380,000 years after the Big Bang, everything was like the equivalent of the surface of a star. 10 minutes after the Big Bang, everything was like the interior of a star. And it's like it shows you this smooth line. And then we see like a ton of other independent lines of evidence, the baryonic acoustic oscillations, the polarization of light in the cosmic microwave background radiation. It goes on and on and on. And each time scientists come up with sort of, they discover another line of evidence that slots into this observation that the universe is getting less dense over time. But the Big Bang never says where the universe came from. We don't know where the universe came from. All we know is that if you run the math and if you sort of consider the observations, you get to a time when the entire observable universe was an object the size of a grapefruit. And that there was more universe outside of that, but what we can see today was once the size of a grapefruit, or maybe the size of a volleyball, right? That's it. That's the end of the inquiry. Why was it so dense? We don't know. What was before that? We don't know. What caused it to start becoming less dense over time? We don't know. And so really any alternative theory has to answer all of those lines of evidence and then has to explain flaws in the Big Bang, which there are some, right? There's sort of the lack of magnetic monopoles. There is the flatness of space. There's like a bunch of issues that people who work with the Big Bang understand. And like inflation has been one method to try and solve that problem. But any other theory has to explain the discrepancies in the Big Bang. Then it has to make new, original, testable predictions about the universe that says, well, if you just go and look at this, and if you look over there, you should see this. And so it will fully explain all the observations that we already have. It'll explain some, if not all, of the mysteries that have already been identified. And then it makes these new testable predictions that can then be followed up. And so that is a really tall order for any new alternative theory to the Big Bang to be able to overcome. And a lot of the times when people pitch theories about alternatives to the Big Bang, they are missing out all of that work that needs to be done. Explain the current observations, fill in the missing gaps, make testable predictions. It's more like, I've just got this feeling that it just isn't right, man. That doesn't get you very far in the world of science. So if a really interesting theory comes along that does all of that, I will be all over it. I can't wait. That sounds amazing. Because that's exciting. I think it's really funny to me that people think that scientists or, people like me, we just want to follow the Big Bang scientism philosophy as religion. And that couldn't be further from the truth, right? That's boring. What do you know? We found another observation. It matched our predictions. Yawn. Right? No, what we want things that are new and weird and different, and it shakes things up, and you're always on your toes. And I've got new, totally upside down stories to report. I wish. That sounds great, but we don't get that. We get the universe that we're in, where the lines of evidence are carefully constructed, figured out, measured, obsessed over, and they are falling into place into this and sort of getting harder and harder for alternative theories to be able to find a toehold. So I can't wait to find out that everything I knew was totally wrong. That's exciting to me. I think people don't realize how much I love things to be new, different, weird, unsettling, flipped upside down. I am an agent of chaos, in my personal life. Just ask people around me. But you gotta wait for the evidence to show up before you change your mind like that. All right, those are all the questions that we got this week. Thank everyone who went into the YouTube comments and put in your question. I get a lot of questions from people who are like, where do I put in my question? And you did it. That was your chance. And that was your question. Weird. But yeah, any YouTube video, just put in a question. I see them all. I see everything. But we also record the show live every Monday at 5 p.m. Pacific time. So if you want to come and join the live show, it is 2 hours long. And you're only watching an edited down version from the first half. Imagine the extra content. And of course, we put a link to every single one of the full unedited 2-hour live streams over on our Patreon, which you can subscribe for free. If you just go to patreon.com/universe today and you follow us for free, you'll get the links to all of the QAs, and you'll get every episode of the QA and a link to the full unedited live stream. So if you want to see all of the content that you're missing, that's the way to do it for free. All right, I'm going to talk about my upcoming schedule, but first I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Barry Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, ScienceWorldRecord.org, Spiderswap.io, Stephen Krasaki, Stephen Filer Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So just one quick note, I'm going to be here next week, but then I'm going to be gone for a week. I'm going to be going on a trip with my other kid to Iceland and Amsterdam. So I will be here for one more week and then I'll be gone and then I will be back and I will report. But the hope is that I will see some auroras in Iceland and I will try to take some photos and some videos while I'm there. I haven't been to Iceland in a couple of years, and last time I was there, it was pretty close to solar minimum, but now we are approaching solar maximum, and so theoretically it should be a really good view. So I will let you know how that all turns out. All right, we will see you all next week, and then no show for the week after that.